We watch the dark for visitors. We build our machines to listen for whispers and look for ghosts, tracking the orbits of silent wanderers that come and go from the cold edge of everything. We map their paths. We predict their arrival. But what happens when a giant, one that promised a spectacle not seen in a generation, a comet predicted to burn brighter than the brightest star in the sky, simply falls apart in the dark? What happens when our most powerful eyes, our planetary radar systems designed to paint a picture of these travelers, get nothing back but static? In the year 2019, we found an object hurtling toward the sun. We named it Atlas. It was supposed to be a triumph. Instead, it became a warning, a lesson in cosmic fragility. It was too far, too faint, too ready to die. And the reasons why reveal a truth not just about this one comet, but about the very nature of the ancient bodies that haunt our solar system. This story is about a ghost, a comet that broke its promise and vanished into dust, leaving behind a trail of questions. The fact that it was too distant for our radar to even see is not a failure of our technology. It is the critical first clue to understanding what it truly was. If you value documented deep dives into the mysteries of our solar system, subscribe to this channel. It's the single best way to support our work. Also, let us know in the comments what city you're watching from. The information you're about to hear is pieced together from observational data and subsequent analysis published by teams across the globe, including detailed reports in the Astrophysical Journal letters and data released from the Hubble Space Telescope's specific observation program for this event, GO 15949. This is the documented story of the comet that fell apart. Now back to the information. It began on the night of December 28, 2019. A robotic eye, a 0.5 meter telescope at the Mauna Loa Observatory in Hawaii, recorded a faint smudge of light, a barely perceptible haze moving against the starfield. This was one half of the Asteroid Terrestrial Impact Last Alert System, or ATLAS. Its twin telescope on Haleakala was also part of the network. Their prime directive, funded by NASA's Planetary Defense Coordination Office, is to scan the entire visible sky every 2 nights, hunting for asteroids that could pose a threat to Earth. In the course of this relentless, automated watch, they discover thousands of supernovae and hundreds of comets. This new smudge was given the provisional designation C/2019Y4 Atlas. The C marked it as a long-period comet, a visitor on a journey lasting more than 200 years. The announcement was logged by the Minor Planet Center, the global clearinghouse for all such discoveries. At first, it was just another faint object on a long list, one of dozens found that year. But when astronomers began to plot its trajectory, the story changed dramatically. A team of astronomers, running the initial data through Orbital simulation software, found a ghost in the machine, the comet's path through the solar system. Its orbital elements were a near-perfect match for another downwing, much older visitor, the Great Comet of 1844, officially designated C/1844Y1. That comet had been discovered by Ignacio Mauvet at the Paris Observatory and had become a spectacular sight, visible to the naked eye for weeks. To a celestial mechanist, an orbit is a fingerprint, defined by specific numbers: the perihelion distance, the point of closest approach to the Sun, the inclination, its tilt relative to Earth's orbital plane, the longitude of the ascending node, and the argument of perihelion, which define the orbit's orientation in 3-dimensional space. When they compared the two, the numbers were almost identical. Comet Atlas had an inclination of 45.3 degrees. The 1844 comet was at 45.5 degrees. The perihelion distance for Atlas was 0.25 astronomical units. For the 1844 comet, it was 0.24 s. The other elements were just as close. This was no coincidence. The odds of 2 unrelated comets from the outer solar system having such a similar fingerprint are astronomically small. This meant they were related. They were siblings, fragments of a much larger parent body that had shattered, likely thousands of years ago, sending its children on vast, looping paths back out into the void. The comet of 1844 was one of those children, and now another had returned. The hype machine began to turn, and for good reason. Based on its trajectory, Atlas was going to swing incredibly close to the Sun, just 37.8 million kilometers, well inside the orbit of Mercury, on May 31, 2020. As it got closer, the Sun's heat would vaporize its ices, water, carbon dioxide, carbon monoxide, creating a huge, expanding atmosphere called a coma, and a tail of dust and gas that could stretch for millions of kilometers. Early predictions, based on its initial rate of brightening, were astonishing. Some astronomers speculated it could reach an apparent magnitude of +2 or even 0, making it as bright as the stars Vega or Arcturus. Then, as it continued to brighten aggressively through February and into March, the estimates got wilder. By the time it made its closest approach to Earth in mid-May, it could hit a magnitude of -5. That's brighter than the planet Venus, the third brightest object in our sky after the Sun and the Moon. It would be an object visible during the day, a true great comet, the kind that gets recorded in history books and remembered for a generation. For months, it seemed to be following the script. Through January and February of 2020, it brightened 4,000-fold from its discovery magnitude. Amateur astronomers with backyard telescopes could easily spot it. Its coma grew enormous. Estimated at over 720,000 kilometers in diameter, are about half the size of the Sun, even though the nucleus within was only a few kilometers across. It glowed with a distinct greenish hue, the telltale sign of diatomic carbon and cyanogen molecules in the coma being fluoresced by the Sun's ultraviolet light. Everything was pointing to a spectacular show. Then, in the last week of March, something went wrong. Professional and amateur astronomers tracking the comet nightly noticed a change. The rate of brightening, which had been so steady, so predictable, slowed dramatically. For a few days, it plateaued. Then, it began to fade. This was the opposite of what should have been happening. As it raced closer to the Sun, the heating should have been intensifying, the outgassing growing more violent, the comet's light growing ever brighter. But Atlas was getting dimmer. Something was happening to the engine. The core, the nucleus of the comet, was in trouble. On April 2nd, the amateur astronomer José de Queiroz from Portugal reported a crucial visual confirmation. The comet's central condensation, the bright, almost star-like point of light that marked its nucleus, was no longer a point. It was elongated. It looked blurry, stretched out into a small bar. This was a catastrophic sign. It meant the solid, icy heart of the comet was likely breaking apart under the strain. The show was over before it had even begun. The great comet of 2020 was dying. Confirmation came swiftly from around the world. On April 5th, a team using the Lulin 1-meter telescope in Taiwan imaged the comet and saw a scene of complete disintegration. The nucleus was not just elongated, it had shattered into at least 3 distinct pieces, all shrouded in a chaotic and fan-shaped cloud of dust. The dream of a daylight comet was dead. In its place was a new, urgent scientific mission, to watch a comet die in real time and figure out precisely why. The world's most powerful telescopes turned their gaze toward the fading ghost. A request was sent through the Director's Discretionary Time program to activate the Hubble Space Telescope. Its unparalleled sharp vision, orbiting high above the blurring effects of Earth's atmosphere, could dissect the chaotic scene and resolve the individual fragments. The observations were approved under the program ID GO 15949 DARS, with principal investigator Quanji Ye of the University of Maryland. On April 20th, 2020, Hubble's Wide Field Camera 3 stared at the wreckage. It saw not 3 pieces, but something closer to 30 distinct fragments. 3 days later, on April 23rd R, it looked again. The scene had changed completely. Now, there were only 25 fragments left. The pieces themselves were unstable, continuing to break down and fade away into nothingness over the course of hours and days. Hubble's resolution allowed for an estimation of their size. The chunks were no larger than an American football field. Many were just the size of a house. This was not a solid, monolithic body that had cracked under pressure like a dropped piece of china. This was something far more fragile, something that had simply crumbled into dust like a dry sandcastle. This is where our other set of eyes comes in, or rather, where they couldn't. Planetary radar is one of the most powerful tools astronomers have for studying near-Earth objects. By transmitting a powerful beam of radio waves from a massive antenna and then capturing the faint echo that bounces back, scientists can learn incredible details. Radar can map the surface of an asteroid, determine its exact size and shape to a precision of a few meters, measure its rotation speed and wobble, and even get clues about its composition, whether it's solid rock, porous rubble, or rich in metals. The 2 premier facilities for this work were the Arecibo Observatory in Puerto Rico, with its gigantic 305-meter dish and 1-megawatt transmitter, and the Goldstone Deep Space Communications Complex in California, with its 70-meter antenna and a 500-kilowatt transmitter. They can produce images of asteroids that rival those taken by spacecraft flying right past them, so why not use them on Atlas? The answer is simple, and it is the key to this entire story: distance. Radar is an active system. It has to provide its own illumination. That signal has to travel all the way to the target, bounce off, and then travel all the way back. The strength of that returning echo is brutally governed by the laws of physics. Specifically, the signal strength is inversely proportional to the fourth power of the distance. And this is a punishing law. If you double the distance to a target, the radar echo you get back is not 1/4 as strong. It is 16 times weaker. Triple the distance, and it's 81 times weaker. There's a very real, very hard limit to how far you can see. For planetary radar to get a good, detailed return, a high signal-to-noise ratio from a dark, non-metallic object like a comet, the target needs to be within a few tens of millions of kilometers. When Comet Atlas was breaking apart in April of 2020, it was over 146 million kilometers from Earth. That is roughly the same as the distance from the Earth to the Sun. At that range, the round-trip light time for the radar signal was over 16 minutes. The echo, if any returned at all, would have been hopelessly faint, thousands of times weaker than the background radio noise from the galaxy. It would have been like trying to hear a single pin drop in the middle of a hurricane from a mile away. But there's even more to it than just distance. The target itself matters immensely. Radar works best on solid, reflective objects. A metallic asteroid is a fantastic radar target. A big, solid, rocky one is pretty good too. A comet nucleus is a challenge. They are not solid rock. They are a mixture of ice, dust, and rock, often with a very dark, unreflective, porous surface. They are often called dirty snowballs, or more accurately, icy dirt balls. Their surfaces absorb much of the radar signal rather than reflecting it. Now, consider what Atlas had become. It was no longer a single nucleus, however weak. It was a diffuse cloud of house-sized chunks and fine-grained dust spread out over tens of thousands of kilometers. There was no single solid object to target. Trying to get a radar echo from the shattered remains of Atlas would be like trying to get a radar echo from a cloud of smoke or a puff of steam. There's just nothing solid enough to provide a clean, coherent reflection. The signal would mostly pass right through it or be scattered in all directions by the tiny dust particles. So Atlas was not just too far, it was also too faint, too diffuse, too ghostly a target for radar to ever see. This failure, this inability to use one of our best tools, forced science to adapt. It meant that every other piece of information, every photon of light captured by telescopes like Hubble, became infinitely more precious. Without radar to give us the ground truth of the comet's physical structure, astronomers had to tease the story from its light alone. They used photometry to measure the brightness of each individual fragment over time. This told them how quickly the fragments were themselves disintegrating. Some faded away in a matter of days, confirming they were not solid, icy bodies, but were instead loose collections of smaller pebbles and dust that were rapidly sublimating in the sunlight. They performed spectroscopy, breaking the comet's faint light into its constituent colors with instruments like the Neil Gehrels Swift Observatory. This is a chemical fingerprint. It told them what molecules were present in the gas cloud. They found the usual suspects for a comet, cyanogen, diatomic carbon, but the sheer volume of dust produced relative to the gas was also a clue. It pointed to a body that was perhaps dust-rich and ice-poor, or at least one whose ices were so volatile they vanished almost instantly, leaving the dust behind. The meticulous analysis of the Hubble data, led by astronomers like Quanji Ye and David Jewett at UCLA, painted a picture of a profoundly weak object. They calculated that the force needed to pull the nucleus apart was tiny, the gentle, steady push of sunlight vaporizing ice on one side of the nucleus, creating a minuscule jetting force. Might have been enough to spin the comet up until it just fell apart. It didn't need a violent explosion or a collision. It was so fragile that the simple act of approaching the sun was a death sentence. It was like a snowball made of loosely packed powder, which dissolves into slush at the first touch of warmth, rather than a solid block of ice that melts slowly. This profound structural weakness is the first major revelation about its true nature. Many comets that come from the Oort cloud, the vast spherical shell of icy bodies at the outermost edge of the solar system, are thought to be dynamically new. This means they have never, or have only rarely, ventured into the inner solar system before. They are pristine relics from the dawn of everything 4.6 billion years ago. They haven't been baked and hardened by repeated passes near the sun. Atlas was one of these. It was a primordial weakling. Its journey over billions of kilometers, from the cold, dark past to the orbit of Neptune and Jupiter and Mars, was its first and its last. It did not have the structural integrity to survive the final leg of its journey. The fact that it was too far and too broken for radar wasn't just a logistical problem, it was a direct consequence of what the comet was. An ancient, fragile messenger from the formation of our solar system that disintegrated before it could deliver its message. The ghost had shown itself, not as a bright light in the sky, but as a collection of fading embers, and the study of those embers was just beginning. The story of a comet is written in dust and light, and the final chapter of Comet Atlas was a lesson in translation. The light told us it was dying, the dust told us how. But to truly understand the cause of death, to perform a cosmic autopsy from 100 million kilometers away, astronomers had to move beyond observing the aftermath and begin to model the unseen forces that had torn the nucleus apart. The ghost of Atlas, in its spectacular and premature demise, was offering a rare glimpse into the heart of cometary fragility. The reasons for its death were not singular, but a cascade of failures, a conspiracy of physics acting upon a body that was never built to last. The first culprit is the most fundamental force in the cosmos, gravity. Not the simple pull of the sun that guided the comet on its multi-millennial path, but the sun's differential gravity, its tidal force. It is the same force that a full moon exerts upon the Earth's oceans, raising the tides. Gravity weakens with distance. So the side of a body closer to the sun feels a slightly stronger pull than the side farther away. For a large, solid object like our planet, this stretching force is negligible. But for a comet nucleus, a loose agglomeration of ice and rock held together by forces barely stronger than a sandcastle's, this gentle, persistent stretching can be fatal. As Atlas plunged closer to the sun, the tidal stress increased relentlessly. Imagine taking a ball of loosely packed snow and pulling on opposite sides. It doesn't take much effort before grains start to shift, cracks begin to form, and the entire structure loses its integrity. This is what the sun was doing to Atlas, hour after hour, day after day. It was a slow, inexorable execution, pulling the nucleus apart thread by thread. But this tidal stress was likely only part of the story. The Hubble data, showing dozens of small fragments rather than 2 or 3 large ones, pointed to a more dynamic, more violent end. This brings us to the second culprit, the comet's own activity. The very process that was supposed to make Atlas a magnificent spectacle was also the engine of its own destruction. As sunlight beat down on the nucleus, it didn't just warm the surface, it caused the ices embedded within to sublimate, to turn directly from a solid into a gas. This gas, erupting from fissures and vents on the surface, creates jets of dust and vapor that form the coma and tail. These jets, however, are not uniform. They erupt from active regions, weak spots on the surface, and because the nucleus is a lumpy, irregular body, these jets are almost never perfectly aligned with the comet's center of mass. Each jet acts like a tiny, off-center rocket engine. And if you have tiny rocket engines firing from random points on a spinning object, you don't just push it forward, you start to change its spin. This phenomenon, known as the Yarkovsky-O'Keefe-Radzievsky-Paddock effect, or YORP, is a powerful force for small bodies in the solar system. Over thousands of years, these tiny, persistent torques can dramatically alter an asteroid's or comet's rotation. In the case of Atlas, the process was happening on an accelerated timescale. As it neared the sun, the outgassing became more and more violent. The tiny rocket engines more powerful. The comet began to spin faster and faster. An ice skater can increase their speed by pulling their arms in. Atlas was being spun up by the very material it was shedding. A tipping point was inevitable. At some rotational speed, the centrifugal force trying to fling the comet's material out into space would overcome the nucleus's own feeble gravity and its weak internal cohesion. The entire structure would fail catastrophically. The blurry, elongated shape seen by José de Queiroz was the final, agonizing moment before this rotational breakup, the nucleus stretching to its breaking point before shattering into the 30-odd pieces that Hubble would later count. It had spun itself to death. There is a third, more insidious mechanism that likely contributed to this structural failure. Thermal stress. The environment Atlas was entering was one of unimaginable extremes. The side of the nucleus facing the sun would be heated to well above the boiling point of water, while the side facing away remained locked in the deep cold of space, hundreds of degrees below zero. This immense temperature gradient would create enormous stresses within the nucleus, much like a glass taken from a freezer and plunged into hot water. The material would expand and contract at different rates, creating deep fractures that propagated through the comet's core. Each rotation was a cycle of extreme heating and cooling, weakening the internal structure, creating new cracks for volatile gases to escape through, which in turn accelerated the spin. It was a fatal feedback loop. Tidal forces were pulling it, rotational forces were tearing it, and thermal stress was cracking it from the inside out. The chemical nature of the ices themselves provides another crucial clue. Comets are not just made of water ice. They contain far more volatile compounds, supervolatiles like carbon monoxide and carbon dioxide, which vaporize at much colder temperatures. As Atlas approached the Sun, these ices, buried deep within the nucleus for billions of years, would have begun to sublimate. Pockets of high-pressure gas would form inside the comet, searching for a way out. This could lead to localized explosions, popping off chunks of the surface, or it could build until the pressure overwhelmed the nucleus entirely, causing it to disintegrate in a single energetic burst. The sheer amount of dust seen relative to gas in the comet's remnants suggested that this rapid sublimation of volatile ices may have been the primary driver, flash boiling away and leaving behind a cloud of incoherent dust and rock. Atlas wasn't a solid block of ice melting slowly. It was more like a stick of dynamite with a very long, very slow-burning fuse, a fuse that was lit the moment it began its final journey toward the Sun. The death of Atlas was not just the end of one comet, it was a reunion. As astronomers refined the orbits of the shattered fragments, they also refined their understanding of its relationship to the Great Comet of 1844. The orbital fingerprints were too close to be a coincidence. They were siblings, born from the breakup of a much larger parent body. By tracing their paths backward in time, celestial mechanists can estimate when they were last at the same point in space. The calculations point to a schism that occurred thousands of years ago, perhaps as long as 5,000 years in the past. At some point during a previous trip through the inner solar system, a truly gigantic protocomet, perhaps 100 kilometers in diameter or more, met a similar fate to Atlas. Perhaps it passed too close to the Sun or Jupiter. Or perhaps its own internal activity tore it apart. It shattered, and its children were cast onto nearly identical orbits, vast, looping paths that would take them out to the edge of the solar system and back again. The Great Comet of 1844 was the first of these children to return and be recorded by modern science. It was likely a larger, more robust fragment, one that was able to survive its perihelion pass and put on the spectacular show that earned it its name. Atlas was its smaller, weaker sibling. And the question that hangs in the void is, how many more siblings are there? Are there dozens of other fragments of this ancient, shattered giant still out there, following the same ghostly path? Will we, in a century or a millennium, see another C/something Atlas family comet appear in our skies? Will it be a robust survivor like its 19th century ancestor, or another fragile ghost like Atlas? This family of comets represents a river of debris flowing through the solar system, a stream whose source was a cataclysm that happened when humans were first building cities of mud and stone. To understand the significance of Atlas's fragility, it helps to place it in context with its peers. The solar system is a violent place, and comets have been dying for billions of years. In July of 1992, astronomers Carolyn and Eugene Shoemaker and David Levy discovered a strange, squashed-looking comet in orbit around Jupiter. Comet Shoemaker-Levy 9 was not a single object. It was a string of pearls, a train of more than 20 fragments flying in close formation. 2 years earlier, it had passed so close to Jupiter that the planet's immense tidal forces had ripped its nucleus to shreds. The comet had been killed by gravity. In July of 1994, the world watched as those fragments, one by one, slammed into Jupiter's atmosphere, creating dark scars larger than the Earth. Shoemaker-Levy 9 was a dramatic demonstration of what happens when a comet gets too close to a giant planet. Atlas, by contrast, demonstrated what happens when a comet that is already weak gets too close to the Sun. It didn't need the overwhelming power of a Jupiter. The gentle persuasion of sunlight and its own internal flaws were enough. Just a few months after Atlas disintegrated, a different story unfolded. In March of 2020, a comet designated C/2020 F3 Neowise was discovered by NASA's Wide Field Infrared Survey Explorer Space Telescope. It, too, was on a path that would take it very close to the Sun. Given the fresh memory of Atlas's failure, many astronomers were cautious, predicting it might also fall apart. But Neowise did not fall apart. It survived its perihelion passage on July 3rd and exterior, emerging into the morning sky as one of the most beautiful naked-eye comets of the 21st century, its brilliant dust tail and fainter ion tail gracing the skies of the northern hemisphere for weeks. Why did Neowise survive where Atlas failed? The answer lies in the immense diversity of comets. Neowise may have had a larger, more compact nucleus. It may have been composed of less volatile materials, or it might have been a dynamically older comet, one that had made previous passes through the inner solar system. Each pass acts as a trial by fire, boiling off the most volatile surface ices and hardening the nucleus, leaving behind a more durable, devitalized core. Atlas was dynamically new, a pristine piece of primordial fluff on its very first trip to the crucible. It was like comparing a hardened brick to a ball of cotton candy. One was built to withstand the heat, the other was destined to dissolve. The success of NEOYs, coming so soon after the failure of Atlas, was a perfect lesson. To understand comets, you cannot study them as a group. You must study them as individuals, each with its own history and character. This idea of cometary families, of which the Atlas 1844 group is one, is not new. The most famous are the Kreutz sungrazers. This is a massive family of comets, all sharing an almost identical orbit that brings them incredibly close to the Sun, often just a few 100,000 kilometers from its surface. They are all thought to be fragments of a single, colossal comet that broke apart over 2,000 years ago. Hundreds, if not thousands, of these tiny fragments have been observed, many by the Solar and Heliospheric Observatory, or SOHO, spacecraft. Most are just a few meters across and are vaporized completely as they make their final plunge. Occasionally, a larger member, like Comet Ikea-Siki in 1965 or Comet Lovejoy in 2011, survives its passage to become a truly great comet. The Kreutz family shows us that the breakup of a parent body is a major source of new comets. Atlas confirms that this process is ongoing, happening to comets from all types of orbits, and that the children can be profoundly different from one another. So, what is the ultimate legacy of the comet that fell apart? It is a story of triumph born from failure. The fact that planetary radar could not see it was not a technological shortcoming, but the most important data point of all, it confirmed, without a doubt, that the target was not a single, solid object. It was a ghost. The subsequent observations by Hubble and other great observatories became an unprecedented real-time dissection of a dying comet. We didn't need a mission like Deep Impact, which famously fired a projectile into Comet Tempel 1 to see what a comet was made of. Atlas simply opened itself up for us, revealing its innermost secrets as it dissolved into nothing. The data gathered from its fading light allowed astronomers to test and refine their models of cometary structure. The profound weakness of the nucleus was a stunning confirmation of the primordial rubble pile hypothesis. This theory suggests that the first planetesimals in the outer solar system did not form as solid bodies, but as gentle, low-velocity accumulations of ice and dust, creating incredibly porous, low-density objects with almost no structural strength. They were cosmic dust bunnies. Over billions of years, many of these bodies were compacted or melted or processed by heat and collisions, but some, the ones cast out into the deep freeze of the Oort cloud, remained in their pristine, fragile state. Comet Atlas was one of these messengers. It carried within its heart a physical record of the dawn of our solar system, 4.6 billion years ago. It was a message of profound fragility. The message was delivered not by a spectacular flyby, but by the very act of its own self-destruction. The ghost of Atlas lingers. It serves as a stark warning about the hubris of prediction. We can map their paths with exquisite precision. We can predict their arrival to the minute, but we cannot yet reliably predict their behavior. Each comet is a wild card. The next great comet could be discovered tomorrow, or it could be an object we are already tracking, one that unexpectedly survives its journey and erupts into a generational spectacle, or, like Atlas, it could break its promise and vanish into a cloud of dust and questions. The silent wanderers that come and go from the cold edge of everything still hold their secrets close. We build our machines to listen, but the most profound lessons often come not from the triumphant shout, but from the deafening silence that follows when a ghost in the dark simply fades away. The study of those fading embers continues, a scientific seance to understand the life and, more importantly, the death of the ancient bodies that haunt our solar system.